In the last video, we were mainly experimenting with the neural network. We were experimenting the capability of using the neural network to construct the faces log, right? So it's underneath the stratigraphy ribbon, and then we got a neural net. This dialog box um, allows us to train a neural network that can actually allow us to that can eventually predict the faces log for us, right? And we looked at some of the settings. Um, to use the neural network effectively, we need to pay attention to two aspects. One is that if you have used the neural network before, it's purely a mathematical construct, right? So the neural network only treats the wheel logs and the inputs as a collection of points, right? It's just to treat them as data points, a cloud of data points. So the neural network itself doesn't really inherently know what's actually the geological setting for that particular region or for that particular project that you are working on. So most of the time, in fact, most of the time, the logs created by the neural network still needs to be edited. You still need to edit those logs by hand, right? It's very important um, for you to actually look at those logs and make changes based upon your understanding of the local geology and your understanding about the structure in that region. So so you cannot just take the output of the neural network and just sort of use it as it is, right? Most of the time you need to actually look at them and then make changes based upon local geology. And edit those logs is actually quite simple. All you have to do is to make your cursor look like that little brush, right? So underneath the stratigraphy, or underneath the Windows active context aware ribbon, you just select X section editing, right? And then you have a little brush here, pen discrete. Just click on that, and then whenever you actually move your cursor into a into this kind of discrete log track, it allows you to actually make changes. For example, right, if you want to change the boundary of the clay here, or if you just want to change the lithology, right, maybe change it to like silt or something, right? Oh, silt, right? You have to sort of manually edit those logs produced by by the neural network, right? That's one of the things that we need to actually pay attention to. And another thing that we need to pay attention to is that inside of the when we actually try to use the neural network, uh, it's important for us to actually recognize the limitations of the neural network. Usually, you don't want to sort of separate either for supervised or unsupervised. You don't want to sort of separate the logs into like many categories. You don't want to do that, right? So if it's unsupervised, maybe limit it to like less than five or something, five classes. If it's supervised, then this particular log, for example, the log we used as kind of a ground truth, that kind of thing, the kind of a benchmark, right? It has just four categories inside of it, right? So you don't want to sort of use something that's like more than 10 categories. Neural network usually works best if you actually have a very limited number of categories, right? Less than five. Those kind of things the neural network can handle, right? At least the neural network inside the petrel can handle, right? If it's like more than 10 or 20, like hundreds of categories, the neural network won't be able to actually give you a reliable uh, result. One is that the neural network used in petrel is relatively simple, right? Another thing is that the data, the total amount of data that's needed in order to train a neural network with like hundreds of classes is going to be a lot bigger than the data that you actually have access to usually, right? So it's important to limit the number of classes to a very small number, as small as possible. Right? Maybe just like 2 categories or something, sand and clay. That's if the number of categories is or number of classes is small, then the neural network can usually perform better, right? That's two things about the neural network inside of petrel, and when we use those neural networks, we need to actually pay attention to, or at least keep those things in mind when we actually use those neural networks. And in this video, we're going to start to actually extract some features. We'll try to extract some attributes from those wheel-tops data. Right? The utility of those faces logs are going to be more evident when we start to build the structure model and try to populate it with petrophysical properties. So, but for now, let's look at the utility of wheel-tops, right? The wheel-tops that we have picked, or either sort of picked or sort of modified. So the purpose of doing this kind of a wheel log analysis mainly is just the 2 purposes, right? One is to get the wheel-tops, right, to be accurate enough. Another thing is to get the faces logs, right? And before we look at the utility of the faces logs, which is going to be sort of a major thing when we start to sort of build the structure model, let's look at the wheel-tops, right? How we can actually use wheel-tops to extract some useful attributes that allows us to examine this particular region in a slightly more quantitative way, or in a slightly more visually appealing way to understand, for example, some of the characteristics of this particular reservoir, right? Maybe it's a good idea to reduce clutter. Let me get rid of, not exactly get rid of, but hide some of the logs. Maybe I should just go to the, oh, it's not a new template. Maybe I should just go to the template setting and delete some of the tracks, maybe. Now we have just perm, gamma, porosity, and then fluvial phases, right? Okay, and then fit to west, maybe let's it's already fit to west, I guess. And then maybe let's try to now we have a wheel top. Let's still use the wheel tops in plane A. That was the raw wheel top provided to us, right? One of the things that people often care about is sort of the thickness, right? The thickness of a certain kind of a interval, right? So let's look at how we can actually extract the thickness from the wheel tops data, right? Let's turn this thing off. So how do you actually extract the thickness? One of the useful quantities is called the Icicle. Icicle is basically the thickness as a map. The thickness as a map, basically. You are treating the thickness as some kind of map, right? So you are basically looking at the thickness at different locations or different lateral locations. So how do we actually extract the thickness, right? So we have these kind of layers, the horizons, right? One of the most important thing in the wheel tops is the horizons, right? So suppose we want to look at the thickness of the zone that's between base Cretaceous and top Tarbert. How are we going to do that, right? So let's click on base Cretaceous. That's the top surface, right? and make it active so the face is bold. And then we can just right click on top tarbert. Right. As soon as you clicked on top tarbert, you're gonna right click on top tarbert. You're gonna see an option that's called convert to Icicle points. Right. Let's do that. And then it's gonna ask us, do we want to sort of use the filtered whales only? Let's answer no. We want to use all the whales actually. And then we're gonna get a new data that's called top tarbert to base Cretaceous, right? And what's actually inside of this particular data set is actually the thickness. It's actually the thickness of the zone that's between base Cretaceous and top tarbert, right? And we can open a two-dimensional window here. We have a two-dimensional window here, right? Well, now it's displaying the locations of the whales and the whale heads. Maybe it's a good idea to turn off that. Let's turn it off. Cross sections are also displayed. Let's turn off that. Right. Now there's nothing, and let's click on this. Now we should be able to see the points, right? Because this particular thickness map is actually derived for all the whales. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only nine whales. But why is that? Right? We actually have 15 whales, at least 14 whales, right? Because B1 doesn't have any data on it, any log data on it. So why do we have just 9 points here? Right. So this is plane A. So let's right click on plane A and look at the spreadsheets. Let's look at the spreadsheet. So we're trying to actually get the thickness between base Cretaceous and top tarbert, right? Let's just try to use a filter to see if we got. We used this part of the filter to select the whales, right? But now let's use this part of the filter and try to find out base Cretaceous and top tarbert, right? Surfaces. Let's try to filter these two surfaces. A filter based upon these two surfaces, right? So you can sort of see here, A10 has just the base Cretaceous. It doesn't have top tarbert. Right? A15, the same thing. A16 got base Cretaceous and the top tarbert. And then B2, B4, B6, these are all base Cretaceous. B8 has both base Cretaceous and top tarbert, which means that the top tarbert doesn't exist on all the whales. Right? Why is that? How many top tarbert do we have actually? So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's exactly 9 whales that has top tarbert, right? And we have 9 points here. So it means that 5 whales don't have this particular whale top, don't have this top tarbert whale top, right? Don't have the top tarbert horizon, basically. The reason is that the base Cretaceous is actually erosional. So when we actually converted the base Cretaceous into a erosional surface settings, when we converted the base Cretaceous to an erosional horizon type, it actually did some truncation. So at those locations or at those whales where top tarbert actually emerged with base Cretaceous, the top tarbert horizon was truncated. So we have 5 different whales at which top tarbert merged with base Cretaceous. But it's okay. It's okay. That doesn't really matter too much. Let's delete this data. And then what we're going to do is that we're going to re-import the whale top data. Right? It's actually quite easy to do because new whale top folder. Let's just create a new whale top folder and then change its name to say plane C. Info C. And then all we have to do is to actually import our data again. Import on selection. Worldtops type, worldtops ASCII. Right, okay, open. Right, all the configurations are still the same. Okay for all, and then we should get our new worldtops data. Right. Okay, um, so now let's repeat what we did. Let's repeat what we did, right? So the first thing we want to do is to actually activate base Cretaceous, right? And then just right click on top tabard. And then we get this option. So to convert to Icicle points. No. Now we get a Icicle for the zone base Cretaceous. That's the zone between base Cretaceous and top tabard. And now we can look at the data. It's now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now we have like 14 data points, right? And of course, the thickness at some of the data points are going to be exactly 0, but it's okay. It's okay. So attributes, for now, it's just the data points. It doesn't really display what's actually the number, right? The thickness number. So let's right click and select the settings. So now we got the settings for displaying the data points, right? So number annotation here. For now, it's not checked. Let's check it, and then maybe change the font size to like say 20, right? And then apply. Okay. So now we see the numbers. What's being displayed? The numbers that's being displayed here is not really the thickness. It's a Z. If you actually expand this top tabard to base Cretaceous folder, it's not really just one item. It's got a triangle in front of it. So if you expand it, you're going to be able to see the attributes. So the number that's being displayed here is actually Z. It's not really the thickness. If you want to see the thickness, you have to sort of click on this. Now you see the thickness, right? You sort of see the thickness. At some locations, for example here, the thickness is exactly 0, right? 0, 0, 0. So in all those regions, the thickness between base Cretaceous and top tabard is exactly 0 here. So in those regions, the thickness is like a very small, right? Of course, you have some kind of difference, right? TST and TVT. This is true stratigraphic thickness, and this is true vertical thickness. Neither of them is being computed. So the thickness that's being displayed here is just SSTVD. It should be Icicle thickness. It's a kind of vertical thickness. So the thickness being displayed here, it should be similar to TVT, I think. Right. The true stratigraphic thickness is actually the thickness that's kind of perpendicular to the horizon, right? But for now, the horizon is just picked in the whales. It doesn't have a surface yet, right? Sometimes you have to use the seismic data to determine what the horizon's 3D distribution actually looks like, right? If you just look at the whales and you have just like 10 whales on, it's kind of difficult to construct the 3D expansion of a particular horizon because there's just too few data points, right? So in order to actually compute the TST, you really need to know the horizon as a surface instead of just data points. So that's probably just the reason for not having a TST, right? So that's sort of the thickness between these two horizons, but it's kind of displayed as data points. It doesn't. Later on, we're going to construct a surface from those data points. But before we do that, let's try to extract more of those Icicle data points. Now let's do top tabard to tabard 2. Right. again, make top target active, so the face is bold, and then right click on target 2, and then again convert to icicle points. Right. No, again. Let's display this part. Right, that's target 2, and then attributes. Should be able to see thickness, right? Setting, show text annotation, and then change the font to like a 20, right? So you'll be able to see the thickness of the second layer, right? And then let's keep doing it, right? Now let's make target 2 active, right? And then right click on target 1. Target 1, target 2, and then top knees to target 1. So top target basically is target 2 to top target, and then target 1 to target 2, and then top knees to target 1, right? And then knees 1 to top knees. Then our last layer. Okay, now we have extracted all the data points, right? All the icicle points, right? And you can sort of see the icon that's in front of the objects. They are all look like points, right? Those are not surfaces. So let's create a new folder. Let's just call it thickness points. Points, okay. And then let's just drag all those items that we just created into this thickness points folder. Right? So now we have a collection of thickness points, right? And it's actually organized into different layers, right? So top eave to knees 1, and then knees 1 to top knees, and then top knees to target 1, and then target 1 to top target, and then target 2. Target 1 to target 2, right? Target 2 to top target, and then top target to base criticism. So we've got lots of data points, right? And then if you just prefer to look at those numbers, that's okay, right? But sometimes it's better to actually try to come up with a Icicle surface, right? To look at the color instead of the numbers. If that's what you prefer, if in fact most people actually prefer to do that under the stratigraphy ribbon, we've got a button that's called Make Surface, right? And we can click on it, and then we got this Make Surface dialog box, right? This is actually a quite useful dialog box. Every time if you want to create a new surface from, say, a set of points, you can use this button to actually create that surface, right? And then so it's got like two different parts. On the top part, it allows you to specify the input data, and then on the bottom part, you got like different tabs, right? These tabs allows you to configure how the output is going to be generated, right? So for the input data, all we have to do is to sort of select the data in the input pane, and then use this blue arrow to point them in here, right? And now you have inside of this box, you have top target base criticism, right? And then the second thing is the attribute. We're mainly interested in the thickness instead of the z value. It's not really right. So let's change the attribute to thickness, right? Basically, that's two things that we need to actually configure by hand, right? And then you got this particular option that's called a run for all main input in the same folder, right? We have to sort of click on that in order to actually apply the same kind of setting to every sort of thickness points in the same folder, right? So that's the reason that we actually created a folder and then dragged everything into this particular folder. We have this thing. We have this checkbox that allows us to actually apply the same kind of action to everything, to every thickness point dataset in the same folder. Right? Boundary for center. If you have a boundary like a polygon or something, you can point them in there, but usually it's not necessary, right? And now this part is for specifying how we want the calculation to be done, right? There are two tabs that's kind of useful. One is the geometry tab, and then the other one is called the algorithm tab. For the geometry tab, we can specify the grid size and position, right? So for our simple example, let's just use automatic, right? From input data boundary, right? So all those thickness points has its own boundaries, right? Let's just use that. Let's just use that as our boundary, right? And then grid increment. So when the surface is being created, it's not really a geometric or mathematical surface. It's actually just a bunch of data that's kind of distributed on a regular grid, right? So basically, what we are trying to do is to actually infer from this kind of unevenly distributed data points to a evenly distributed data points, right? And if you want a very dense grid, then you can make the X ink, Y ink very small, for example, to like 20 or 10 or something. Then in that case, you're gonna be able to actually create a surface with a very dense mesh. Every 10 points you have one grid point, that kind of thing. Right. But let's just use 50-50 because we don't really have many wells. If you don't have many data points, then the interpolated results are not going to be very accurate. So let's just use a very large grid increment, right? Let's just accept the default. And then let's go to the algorithm tab. What's inside of the algorithm tab is so the only thing that we care about is actually the method for interpolation. What's going to be the method for interpolation, right? Especially for extrapolation. In those big regions, you don't really have any wells to actually control what the value is supposed to be, right? So because this is Icicle data points, so we can use Icicle interpolation, right? It's a specific kind of interpolation algorithm that's kind of tailored to Icicle data, right? And once you have selected Icicle interpolation, it's telling you some other information here, right? But we don't really need to actually make any changes. And then we can just click on OK. If you want to sort of experiment with different settings, you can just click on apply, and then this dialog box will still be here, and then you can change some of the settings. But let's click on OK here. So it's going to close the dialog box and creates. It's actually creating a different folder, right? And the name of the folder is exactly the same as the name of the folder that's used in the used as the for storing the input data, right? So let's turn it off. Maybe let's just change the name to Icicle. Icicle. Maybe if we want to look at the interpolation result, right? This is for the thickness of the zone that's between top Tarbert and the base Cretaceous. And this is for the thickness between for the zone between Tarbert 2 and top Tarbert. But it looks like it's the variations are like huge. especially for those regions, right? So what's going to be the color scale? What's going to be the color scale, right? If you actually activate or make it active, make one of those icicle surfaces active, you're going to be able to see two context-aware ribbons. One is called window, the other one is called surface, right? The reason that you see this particular surface context-aware ribbon is because the object that you are actually trying to examine is actually a surface object. And you can sort of see it from the icon here, right? So the icon here are all collections of points, but here it looks like a surface, right? It looks like exactly like surface, right? So this is actually a surface object, so you get this kind of surface context-aware ribbon. Right? And then if you click on it, it's going to display a collection of tools that's kind of applicable for two-dimensional surfaces, right? And on this ribbon, you're going to be able to see these three buttons for adjusting color tables and displaying the color legend. If you click on that, you'll be able to see a color bar. Right? So the minimum is like 0 and the maximum is like 60. And this is for thickness, top tapered to base criticus. And what's being displayed on this side of the color bar, this thing, is actually a histogram. It's actually displaying the total number of grid points where you have a specific data value. Right? So the number of grid points that has a thickness of exactly 0 is like a significantly bigger, a lot bigger than the number of data points with different thicknesses, right? That's not 0. So that must be for these two regions, right? We got lots of data points that has exactly 0 thickness. Histogram, so by default, both the color legend and the histogram is kind of enabled, right? If you prefer not to see the histogram, you can just click on it, and then the histogram is going to disappear, right? But let's still put it on, right? And then you got color legend settings. This dialog box allows you actually configure how the legend is going to look like, right? So let's not explore this dialog box now. Let's maybe we're going to look at this later on, right? These two buttons are kind of useful, right? Adjust the color table allows you to actually make the color map kind of adapted to the range of the data that you're actually trying to visualize, right? So if you click on it, it should be automatically adjusted to the data range, right? So if you look at the thickness points, let's disable this one and click on this thing. The thickness points actually goes from what? Goes from 0 to like 101.95. It's a huge variation, right? Right. So if you want to adapt your color table to this particular data range, 0 to like 110, this kind of thing, then you just click on this button. Then the data is going to be automatically adjusted to that particular data range, right? Let's turn this thing off, but display the thickness of the second layer, right? For some reason, it's not doing stuff. And another thing that we can actually take a look at is this particular edit global color table item, this button, right? Once we click on it, it's going to give us this kind of dialog box. It allows us to actually adjust how the color table is configured, right? And underneath the colors, underneath the colors tab, we can actually configure what the color is going to be. Right? So you have 3 options: limit defining color table. That's kind of a fixed limit. If you define a fixed color table with a fixed limit, you can use that, right? And then use limits from property template. right? So the property that you are displaying for now, it's a thickness, right? And then there's a template associated with that. You can use the limits from that template, and then it's also fixed, right? And then the third option, that's auto scale color table to data, right? Let's just apply it. Let's click on that and apply it. For now, it's kind of automatic. It's already automatically scaled to that color table, right? Maybe let's just do it. Okay. So now it's automatically adjusted to the thickness, the values of the different thickness, different layer. Color table is automatically scaled. Okay, so use limits defining color table. If you choose limits defining color table, you can use this kind of an arrow to get max from the selected item, which is this thing. Let's see if I can select multiple items. So the minimum is like 0, but the maximum is like 114, right? And then if you want to change, for example, if you want to change for example, the color. Suppose you want to use blue to indicate the 0 thickness, and then use red to indicate the maximum thickness, right? And you can do that also, right? If that's the case, you can. So now blue regions means no thickness at all, right? 0 thickness. Blue now means 0 thickness. But now red regions are going to be maximum thickness. That's like a 110. But this is kind of fixed across all the layers, all the icicles, right? Right. Um, so let's still use auto scale color table to data, right? Let's still go back to that instead of using limits defining color table. Let's just okay, right? In that case, the color scale that's used for displaying every thickness layer is going to be adapted to the data range, to the thickness range of that particular layer, right? And that gives us a better visualization. Um, some of the icons that's kind of listed in the toolbar is sort of a duplicate of those on the ribbons, basically. So suppose if you want to look at the color legends, you can also click from here, right? You have auto legend here, or auto legend here. If you want to turn it off, also. Oh, did I click on the right thing? For some reason, it's not really doing what I was expecting. Oh, I see. So here it's auto legend. On this thing, it's auto legend. That's controlled by this thing. But on this part, if I click on this thing, and then surface, oh, so you have both this button and also this button to control the display of the legend, of the color legend, right? So here I have turned it off, right? But if I want to put it back on, click on this thing, right? So the color legend is like a duplicate button, also on the toolbar and also inside the ribbon. For some reason, my mouse, is that problem with my mouse? And that's one kind of a thickness maps that people may care about, right? People may care about. But let's try to create some more attributes, right? And this Icicle map were pretty much just sort of created from the thickness points, right? And those thickness points were created from the wheel-top data, right? Or created from the wheel-top data. Um, um, and now we have logs, right? For example, in our wheel data, we have this kind of a fluvial phases wheel log, right? We have a wheel log that's called a fluvial phases, right? This fluvial phases wheel log. Let's go back to the wheel section window. That's this log, right? That's this log. Right? And sometimes people care about the thickness of a certain kind of rock, right? For example, people may care about the channel sand, the thickness of channel sand in each different layer, that kind of thing, right? We can try to create that. So how do we actually extract that kind of attributes, right? Again, let's go back to plan C. Maybe let's put the wheel tops on it. Let's go back to plan C. And then we have attributes, right? For now we have a bunch of default attributes, right? But the attributes we're trying to create is not really do not really belong to the default attributes. So let's create a new attribute by right click on it, right? And then we got an option that's called insert new attribute. Right, let's choose insert new attribute. To add the new attribute to the points, it's asking us to choose the type of the attribute. Let's just use continuous. Yeah, let's just use continuous, and then okay. And at this point, we're gonna get a get this dialog box. So we're gonna sort of look at the info tab and later on, but the most important tab is called attribute operations. So if we are trying to create a new attribute from an existing log, we can specify the settings in this attribute operations tab. Right. And then on the top, we have two options. One is called the surfaces, horizons. So what's actually the attribute actually is attached to, right? So suppose we want to extract the thickness of the channel sand, right? It's not really an attribute that's kind of attached to surfaces or horizons. It's an attribute attached to the zones, right? So let's click on the second one, to the zones at level 1. We have only one level, so it doesn't really matter. And then sample from wheel log. We only have like wheel logs there, right? So we don't really have a surface data that actually allows us to sort of obtain the channel sand thickness. And then log to be used, that's fluvial phases, right? Because we're interested in extracting the thickness of channel sand. And treat log as lines. That's okay. That's also okay. But you can sort of look at these the two different options as points and as lines. There are differences, but now let's just use it as points, right? And then you got an average method, most of, and then if you look at, you have lots of options. Right? the averaging method we are interested in is actually thickness of channels end. So let's choose thickness. As soon as you choose the thickness, the tree log as lines becomes gray because this option is meaningless if you actually use the thickness as the kind of a method, right? And then depth scale. For now, the default is like MD, right? But let's change it to SSTVD. That's our vertical track. And then phase is code. 0 is a background flat plane, but that's not exactly what we wanted. We want a channels end, right? We want a channels end. So the code is 1. If you would like to actually specify the cutoffs, min and max cutoffs, you can do that, right? If it has 0 thickness, then the minimum is gonna be 0, right? You don't want to maybe have a minus thickness or something. But let's just forget about this thing, and then let's just click on run. And then as soon as you clicked on run, you're gonna see a new attribute here. That's called thickness of fluvial phases. 1 channels end. Right. That's a new attribute. It's a new attribute. And you can actually display this attribute just like a wheel log. Let's click on it. Right now we got a new track that's kind of shows you the thickness of channels end for each of the different layers or different zones, right? So here you can see the channels end has a larger thickness than at every other location, at every other layer, right? Yeah, so it looks like this is sort of the thickest part, right? And then once you have those attributes defined on the wheels, you can again try to extract them as thickness points, right? So if you pay attention to the yellow boxes, yellow rectangular boxes, square boxes in front of the horizons, you can treat them as filters, basically. You can treat those things as filters. So let's try to kind of extract this kind of thickness of fluvial phases based upon the different layers, based upon those different horizons or zones, right? So let's try to extract the thickness of fluvial phases for channel sand inside of the base Cretaceous to top the zone base Cretaceous, basically, right? So let's click on that, right? And then we just make this zone active and make sure that this box is checked, and then we can go back to the thickness of fluvial phases and then right click on it. And then at this point we're going to have convert to. We're going to have this option that's called convert to, and then we've got like 2 options inside of it: convert 2 points using filter and convert 2 points. What we want to do is to select convert 2 points using filter because we have this thing base Cretaceous as our filter, right? We just want to extract the thickness of channel sand inside of that zone. So let's use this filter. And now we got a new data, new point data out, point cloud, right? If we want to sort of visualize them, we can go back and display it in a 2-dimensional window. Right. So that should give us the thickness of channel sand, right? The thickness of channel sand. And then suppose we want to sort of extract more. Let's try to extract more. So unselect those. Let's select top-toppered, right, and then go back to right click, and then do that again. Convert two points using filter. Right. Now we have a second set of thickness points. Right. And then let's do that again. Toggle 2. Convert to filter. So if we want to look at the numbers, again, we can double click and then go to the style tab and then choose a larger font, 20. Right, so we can see what the thickness actually looks like. What's actually the numbers. So that's toggle 2, right? Let's do toggle 1. And then go thickness again. Where's my convert to? Okay, convert to points. Let's toggle 1, right? And then top knees. And then knees 1. And then top eve. But top eve, I'm supposed to see an error message because there's no zone, right? Not able to convert the points. The reason I'm seeing this particular error message is because top eve is like the bottom horizon. Right? Underneath top eve, there's no more horizons, so there's no zone associated to top eve. For every other interfaces, we have a zone, right? We have a zone underneath it. And the thickness is actually a zone-related property. So that's why we are going to be able to actually get this error message. Right. At this point, we might want to just create another folder to put those data in them. Let's just call it channel send. Channel send thickness points. And then we can just drag those in there. Right. Of course, you can again apply the. Again, you can try to create a surface. You can try to create a surface from that from this data set, right? From this data set. Let's just do that. Make surface, right? Make surface, and then so these boxes, the content in those boxes are from the previous use of this create make surface button. Let's delete it. So let's click on result surface and then press delete on your keyboard. So do you want to reset the settings in the dialog? Yes, I want to reset everything. And then it's going to allow us to reselect all the data, right? So input data, we're going to use plan C, thickness, full faces, channel 10, right? And then we're going to apply for all main inputs in the same folder. And then let's just use automatic grid boundaries. 50 meter, 15 meter, that's fine with me. And then algorithm, for the algorithm, let's use a convergent interpolation. Convergent interpolation is kind of a more stable interpolation algorithm that's unlikely to give you some kind of outrageous values. So let's click on OK. Then it's gonna create the thickness surfaces. And then let's collapse this part, and then let's just display it. So maybe I should adjust the range of the color. Oh, it's already automatically adjusted. So So okay, so it looks like we got a thickness map for channels end inside each layers, right? Maybe we should just change the name from thickness point to thickness surfaces. Thickness surface. And then we can still do the same kind of thing to create other kinds of attributes, right? For example, if you care about porosity, you want to know what's actually the average porosity inside of each zone, right? We can again try to create a new attribute. Try to extract. So now we've created a thickness of fluvial phase channel sand. This is one of the attributes that we have extracted by ourselves, right? And then let's create another one. For example, average porosity for each of the layer. Insert a new attribute, right? Again, continuous maybe. And then let's just go directly to the attribute operations, right? And then again to the zone level. Log to be used. Let's use porosity, right? As lines arithmetic average. Yeah, let's just use those settings, and then click on run. So for porosity, you usually want to use just the arithmetic average. But for permeability or for other kind of attributes, for example, resistance, that kind of thing, that's kind of displayed on a log scale, that kind of thing. You can use either harmonic or geometrical RMS. These three options are usually applied to log data that's displayed on a logarithmic scale, right? But for porosity, usually it's just the arithmetic averaging. And then let's click on run. The important thing is to remember to click on run. Otherwise, you won't be able to actually see this attribute, right? If you just click on OK or apply, it's not going to work. You have to click on run first, right? And then if you go back to the wheel section window, right? You can display porosity, right? So the average porosity, how it's actually distributed inside each layer, inside each zone, basically, right? And again, you can try to extract this porosity as a bunch of data points, and then try to interpolate the surface from it, right? So if that's the case, all you have to do is to, remember, porosity, right? Click on porosity, make it active, and then click on base Cretaceous, right? And select the box in front of it, and then just right click on porosity, and then convert to points using filter, right? And now you're gonna get a porosity data point, and then you can go back to the two-dimensional window and then try to display it, right? See how the porosity is actually distributed on those wheels, right? And then if you care about a different layer, then make that layer active, select that, and then go back to porosity. Convert to the points using filter. Right. And if you want to look at the porosity values, just display the text for example, right? They will be able to see the average porosity for that particular layer, for that particular zone, I mean. So that's top of the one. So let's go back to top knees now. Top knees now. Why my top Eve is selected? Did I extract the thing right? I'm not sure. Maybe I did something wrong. So it might be a good idea to just delete it and then restart again. So I may have done something wrong, I think. So make sure that porosity is selected, and then let's still start from base Cretaceous, and then click on this box, and then right click, and then convert to points using filter. And uncheck this box, click the next one, porosity. Again, convert to, so using filter. Uncheck this box, click on this one. Convert to points, and then uncheck this one, click on this one. Convert to data points, and then the last one, top eve. The last one, top eve, is not supposed to work because it's got no thickness. There's no zone associated with it. Yeah, that's correct. So now we've got a bunch of data points for just the porosity, the average porosity inside of each zone, right? And at this point, we can just try to create another folder. Let's just call it average porosity. Average porosity points. And then we can just drag all those things inside of this folder, right? And again, if we want to sort of interpret the surface out of it, it's we can also do that, right? We can also do that. Make surface, right? Make surface. Let's delete it. Yes. Delete the previous data, and then point the new data into it. And then run for all main inputs, and then automatic. Let's still just use convergent interpolation, and then click on OK. Right. So this way we are supposed to get another surface, another set of surfaces that allows us to actually examine the average porosity. The average porosity inside of each layer, inside of each zone. Right. If you don't like the color table, you can just click on adjust the color table to make the adapted to that, to the data in that particular zone, to porosity distribution in that particular zone. So now we can actually look at the average porosity as a function of the zones. Right. So usually it's actually quite useful to actually examine those data before you actually try to construct a three-dimensional structure model from those data, right? And it's kind of sometimes those kind of attributes allows you to actually discover problems with the data later early on, right? If after you have finished building the model and then you discover some problems, then you have to sort of go back and redo all the model. It's a huge waste of time, and it also hurts the attitude of the worker. So it's kind of important for us to actually extract those attributes, to build those attributes, and then examine those attributes, and try to discover problems, any kind of problems early on, before we actually start to build the structure model, right? And in the next video, we're going to start to actually build the structure model by using a corner point, by building a corner point grid.